Hi everyone, and welcome to the first of two videos going through some past paper questions on enthalpies of solution. Now, enthalpies of solution are linked very much to lattice enthalpy. It's an alternative way of calculating lattice enthalpy. Instead of doing atomizations and ionization energies and electron affinities, we can use enthalpy of solution and enthalpy of hydration to construct a Born-Haber cycle in a different way. So it very much links to the lattice enthalpy questions. As you can see in this first question, we've got what is the definition of lattice enthalpy. Okay, so it definitely is part and parcel with the same kind of topic. So lattice enthalpy, we need to know the definition of this. It comes up all the time. So it is the enthalpy change that accompanies the formation of 1 mole of an ionic lattice from its gaseous ions. And that is a definition that you really do need to learn. Okay. Then here we've got a table with some values. Okay, fine. It's saying, why is the enthalpy change of hydration of chloride ions exothermic? Okay, enthalpy changes of hydration are always exothermic. It's not just chloride. Well, what does exothermic mean? It means it's releasing energy. Okay? And energy is released whenever you're forming a bond or forming an attraction. Okay? And so this is because when we're doing enthalpy of hydration, it's because the chloride ion is forming an attraction to water molecules. Okay? So we can say because energy is released when chloride ions form attractions to water molecules. And that's all we need. It's only a 1 mark question. Right, we then have our actual Born-Haber cycle, and it wants us to fill in the gaps here. So what's going on here then? This process here is our enthalpy of solution. We're starting with our solid ionic lattice. Enthalpy of solution is when you take your lattice and you dissolve it in water, and so you end up with aqueous ions. So here we're going to have magnesium ions, aqueous, and we're going to have 2 aqueous chloride ions. And then these 2 processes here represent the enthalpy changes of hydration, which is going from gaseous ions to aqueous ions. And so we're just doing them one at a time. So this is enthalpy of hydration of magnesium and then of chloride. Or it could be the other way around. There's no way of knowing. It doesn't matter. So I'm going to put magnesium as an aqueous ion here. And I'm going to have my chloride ions still as gases. So that this process then represents the hydration of magnesium. And this process represents hydration of chloride. Okay. But I could do this the other way around. You could have magnesium ions as a gas and chloride ions as aqueous. As long as you've got one of each, it doesn't matter which way around. So we then need to do the calculation. So if we then go back and have a look at the values that it's given us, we know the lattice enthalpy is minus 2493. So the lattice enthalpy is going from gaseous ions to the solid. So that's this one here. We have the enthalpy change of solution is minus 154. We said that was this one here. And the enthalpy change of hydration of chloride is minus 363. So that is this process here, but it's actually minus 363 times 2, isn't it? Because I've got 2 chloride ions. And we're trying to calculate the enthalpy of hydration of magnesium. So this is the one that we want to work out. Okay, so let's have a look. We're just going to write the values down, right? So I've got minus 2493, I've got minus 154, and I've got minus 363 times 2, and I need to decide what am I going to do with those. Okay. So we're trying to calculate this process here. So this is where we're starting, and this is where we're finishing. And we're trying to go that way So therefore we need to go the opposite way round. So we're going to start here and we're going to come down that one. We're going to come down that one, and then we're going to go back up that one to get to our end point. Okay. So then we need to compare the arrows again. So with the minus 2493, our arrows are in the same direction. So we're going to add that one. These two arrows are in the same direction, so we're going to add that one. And then here, these two arrows are in the opposite direction, so we're going to take this one away. And then this is what we're going to calculate. So we're going to do minus 2493, minus 154, and then plus 363 twice. And so we get minus 1921. Okay. Does that seem sensible? Remember, this is not a lattice enthalpy, so we can't just do the, oh, it should be a big negative number, because it's not lattice enthalpy, it's enthalpy of hydration. Okay, but enthalpies of hydrations are also negative, so it should come out as a negative value. It's not necessarily going to be a massive negative value. Now you can see enthalpy of hydration of chloride was only minus 363, but it should definitely be negative. Okay, so we've probably got this right, or at least we've got a chance. So it is worth doing that check. If you get an answer that comes out as positive, then you've definitely done it wrong. Okay, and then finally it says the enthalpy change of hydration of magnesium ions is more exothermic than the enthalpy change of hydration of calcium ions. Okay. Now, if you've seen the previous videos on lattice enthalpy, you will know what this is about. It's the same question. Okay. The two things that affect values for enthalpy changes involving ions are the ionic charge and the ionic radius. Okay. So let's look at magnesium and calcium. If we look at them on the periodic table, magnesium and calcium are both here in group 2. So they're both going to have the same charge. It's the radius that's going to be different. Calcium ions are going to have a bigger radius than magnesium. Okay. So let's say magnesium ions and calcium ions have the same charge, but magnesium ions have a smaller ionic radius. So they have a stronger attraction. And then this is where we need to be careful. If this was lattice enthalpy, we'd be saying they've got a stronger attraction to the negative ions in the lattice. But we're talking here about enthalpy of hydration. So we need to say they have a stronger attraction to water molecules. Okay, because that's what's going on in the enthalpy of hydration.